Now, missing terms. We've been dealing primarily with trinomials, with things that have an ax squared term, a bx term, and a c term. So the quadratic term, the linear term, and the constant term. But there is a chance that this guy has to be there, or else you wouldn't have a quadratic. And since we're talking about quadratics, we need that ax squared term. But it is possible that the bx term might not be there, or the c term might not be there. And generally, when you're missing a term, things do actually get a little bit simpler, a little bit easier to find your solutions or zeros. A lot of times, very basic algebra becomes involved. So for example 9, what we are going to do is we are going to, first of all, circle solutions. By the way, you might want to try this question on your own. Most students should be prepared at this point to solve this question on their own. So if you want to solve it on your own, pause the video and then come back and join us. We need the solutions to this equation here. So I'm going to do this. This might not be what some of you did or some of you expected. I'm going to do this by subtracting the 6x from both sides. Should have done that first, but I'm writing it down now. And then what I'm going to do is what we've done on a couple of previous examples. I'm going to factor out a greatest common factor, and that in this case will be 3x. So what I am left with inside parentheses will be x minus 2. Again, distributing 3x times x, that gives me the 3x squared. 3x times negative 2, that gives me the negative 6x. So I have factored this correctly. Quick distribution tells me that I did. Now, what I'm going to do is I'm going to use the zero product property. I could also use what we talked about a few pages ago. I think on page 136 at the top, we said that if the coefficient is in front of the x is 1, we can just take the opposite of this number here. So we know 2 is going to be one of the zeros or one of the solutions here. But again, I'm going to use the zero product property just to keep this a little bit more formal and a little bit more systematic. 3x equals 0. Remember, I know that if 3x times x minus 2 equals 0, one of those two things has to be equal to 0. That's what the zero product property says. That's what I am doing here. So I get 0. And I get, for this one, as we said a moment ago, I get positive 2. So the two solutions here are 0 and 2. 0 and 2 are the two values of x that will make this equation true. Now, very important, if you do what a lot of students will do on this question, which is divide by x, students will see an x that's common to both sides. They see that if you divide by x, you can get rid of the x on the right and reduce the exponent of the x on the left, and what you end up with is 3x equals 6. And if you divide by 3 and divide by 3, you get x equals 2. And note, 2 is one of your zeros, but the problem with dividing by x is that you lose one of the two solutions. So it is legal to divide by x. It's perfectly fine. It's perfectly allowable to divide by x, but you've got to understand you're going to lose one of the possible zeros. So I do not recommend dividing by x in cases where you are solving for the solutions to a quadratic, because you will lose one of your zeros. I recommend to get all of your terms to one side. This was basically step 1 of the factoring process that we talked about a couple pages ago. Get all of your x terms to one side, get 0 on the other, and then start your factoring. If the middle term, the bx term, is missing, so we have what looks like an ax squared term. Obviously, in this case, the a is our x. And we have a c term. We have a constant term. Usually, regular old algebra will be perfectly acceptable here. What I mean by that is, so we need values of a that satisfy this equation. So we need the values of a that will make this stuff on the left equal to 0. So what I'm going to do is I'm going to add that 121a squared to both sides. I'm going to get, flipping the equation here, I'm going to get 121a squared equals 100. If I want to isolate a, I would divide by the coefficient of a squared first, and I will get that a squared equals 100 over 121. And of course, to get a alone as opposed to a squared, I square root both sides, and I get that a equals, it is important that you know how to make calculations like this without a calculator. You can see we are on a no calculator question here, and you will see stuff like this on the no calculator section, which means you really do need to understand that root 100 over 121, root 100 over 121 is exactly the same as root 100 over root 121, and root 100, of course, is 10, and root 121 is 11. Now, by far, the most important thing that you need to keep in mind on these questions. I'm going to go ahead and highlight this. When you square root a squared variable, you do have to account for both the positive and the negative solution, because it is true that both positive 10 over 11 and negative 10 over 11 when squared will give you 100 over 121. So when we write a squared equals 100 over 121, we have to account for the fact that 10 over 11 squared will give us 100 over 121, and negative 10 over 11 squared will also give us that positive result, that positive 100 over 121. So extremely important that we account for both the positive and the negative, unless of course the question says something like, so I'm going to write down positive negative 10 over 11, unless of course the question says that a is a positive value or something like that. In other words, if the question restricts us to only one of the two values, then we've just got to abide by the question. So that is the answer to example 10. Keep in mind that if you are missing the bx term and both your a and your c terms, okay, this is your a, this is your c, are positive, you're going to get imaginary solutions, because what's going to happen is you're going to end up with 4x squared equals negative 32, right? Because you're going to be subtracting that negative 32 over to the right. And then you, of course, you could also factor out the 4 and try it that way. We did talk about that procedure. If I then square root both sides, actually I'd divide by 4 first, sorry about that. So there we go. And then when I square root both sides, of course, negative 32 over 4 is negative 8. I'm going to be square rooting a negative number, which means that x is going to result in an imaginary number. Square rooting a negative results in an imaginary number. We will talk about the quadratics with imaginary solutions in a few pages. Sometimes if you're missing a bx term, you will yield the form x squared minus y squared, which is known as a difference of squares. Why is it known as a difference of squares? Because you are subtracting two things and therefore yielding a difference, and you have two perfect squares being subtracted. So difference of squares. Pretty obvious stuff there. Almost every one of you should know what a difference of squares factors into, so I wouldn't even watch me do this. I would try to factor x squared minus y squared before you see me do this. I'm going to do it right now though. Pause the video if you haven't already. So I've got two factors, and of course the difference of squares is always going to factor into x plus y times x minus y. In other words, the square root of the first term here, the square root of the second term, there's the first term, there's its square root, there's the second term, there are its square roots, and then we have one positive, one negative. All differences of squares factor into this form, x plus y times x minus y. In fact, on number 10, some of you may have already noticed, a lot of you probably didn't, however, that this is a difference of squares. 100 is 10 squared, and 121a squared is 11a squared. So that is, let me clean that up a little bit, that is a difference of squares. So remember, we also could have done example 10 in this way, where we took the square root of the first term and put it in those two first positions. That's the square root of 100. We take the square root of the second term, which is 121a squared. The square root of that is 11a. And we have one positive, one minus. And of course, if we were doing the zero product property here, we would be setting 10 plus 11a equal to 0. Subtract the 10, subtract the 10. 11a equals negative 10. Divide by 11, divide by 11. There was one of the solutions we got. Then 10 minus 11a. If that were to equal 0, I'll add the 11a. I think that's going to be easier here. 10 equals positive 11a, divide by 11, divide by 11, and of course there's the positive solution. So perfectly acceptable to do a question like example 10 using a difference of squares. I suppose the only tricky part is spotting that you are dealing with a difference of squares. As long as you spot it, you should be able to use that very nice, neat pattern. At the top of the next page, let's practice factoring a difference of squares. So example 11, we need to express 8x squared minus 18 in factored form. So we want this in factored form. Important note, anytime we're going to do fancy factoring like differences of squares or even that X method that we learned a few pages ago, in fact the first step you will recall, first or second step of that factoring method we learned, we always want to start by trying to pull out greatest common factors. Pull out greatest common factors first. So in example 11, that's what we want to do. We can see that there is a 2 common to both of these terms, 8x squared and 18. So I'm going to pull the 2 out first. Where do I want to write this? I'll write it over here. So we've got 2 times 4x squared minus 9. Distributing that 2 back through, that's 8x squared minus 18. Yes, that's correct. And now it should be clear that we have a difference of squares. 4x squared is 2x squared, 2x squared, and 9 is 3 squared. So indeed, we do have a difference of squares. Remember that a difference of squares always factors into square root of the first term, which is that 2x, square root of the second term, and then square root of the first term, square root of the second term again, 1 plus, 1 minus, and we're done. The 8x squared minus 18, the original expression, can be factored into 2 times 2x plus 3 times 2x minus 3. Of course, we should FOIL this all back through, distribute this back through, so we get 4x squared minus 6x plus 6x, so the 6x's will cancel out, and then we have plus 3 times negative 3. So indeed, we do get that 4x squared minus 9, and if we were to distribute that 2 back through, we already did that, we would get 8x squared minus 18. A lot of students are under the assumption that a difference of squares only works when you have really nice, neat, perfect squares. It is generally true that you only want to factor using this difference of squares method when you have perfect squares. However, you should be aware that difference of squares actually works with all differences, whether you have perfect squares or not. For instance, if I wanted to do 7 minus 5, of course, I would just say that that's 2 normally. But if I go in my calculator and I actually type in parentheses square root of 7 minus square root of 5 in my parentheses, and then do square root of 7 plus square root of 5. So really all I'm doing here is I am writing 7 minus 5, that difference, almost as I would if these were perfect squares, right? Square root of the first term, square root of the second term, 1 minus, 1 plus, and when I hit enter, of course, I get 2. So technically you can factor a difference using this difference of squares factorization pattern, and College Board actually has played around with this once or twice, so it's important that you know how to do this. On example 12, if you want to try this on your own before you watch me go through it, that's perfectly fine, although this one will be a little bit unfamiliar to a lot of students. So we need to, again, get the factored form of 27x squared minus 3k. Remember, we always pull out the greatest common factor first, and in this case we do have a 3 that we can pull out. So we get 9x squared minus k inside the parentheses, distributing the 3, 27x squared, negative 3k. Yes, we're good. We factored that 3 out correctly, so that's great. Now, we do have what looks like a perfect square here, right? 9x squared is 3x squared, but k itself does not look like a perfect square. But remember that the square root of k is just root k. So in the same way that I'm going to put the square root of 9x squared in that first position of my two factors, I'm just going to put the square root of k in the second position, 1 plus, 1 minus, and this should do it. If I distribute this back through, 3x times 3x is 9x squared. 3x times negative root k will be negative 3x root k. then I would have, that looks like an x rather than a k, then I would have positive root k times 3x. Well, that's just going to be plus 3x root k. And then, of course, positive root k times negative root k is going to be negative k. These two middle terms will go away, and I will be left with 9x squared minus k with the 3 on the outside, which is indeed what we had right there. And if I distribute the 3, we already did that. We know we're going to get back this original expression. So 27x squared minus 3k can be factored using differences of squares and that difference of squares pattern into this. And we are done. So those are the ways that we will deal with ax²+bx+c form when either the bx or the c is missing.